So on the next page, we're going to take a look at two more examples to help us find the derivative of a function. But these are going to be a little bit more involved because notice how we're going to be utilizing a square root and a rational function. They're not going to be as simple or straightforward as the ones on the previous page were because it was a line and a parabola. So don't get too worried about these, but we're still going to utilize the same limit set up for our derivative. We're just going to apply it to more advanced functions. So if we want to find the derivative of this square root function, we're going to first plug in x plus h in for all the x's in the function, and notice how we would still have the plus 2 on the inside. We then have to subtract the original function, which would just be the square root of x plus 2, and that's all over h. So if we think about kind of our limit thought process or the flow chart that we did at the beginning of the year, normally we would plug in 0 first, but notice how we would have the square root minus the square root, so that would be 0, and we'd have a 0 on the bottom. So we got to ask ourselves, what are some other things we can do to kind of get around this 0 over 0 issue? And hopefully by just looking at our limit set up right now, since we have a square root, we should be thinking a conjugate. So let's go ahead and multiply by the conjugate, which would be the square root of x plus h plus 2, and then we'll add the other square root. So we're going to multiply that on top and bottom to keep our fraction balanced. So hopefully you can write a little bit smaller or keep it in the box, but my pen's write a little thick, so I have to go into the other example. So if we were to actually multiply that conjugate up top, the outside and inside terms would cancel out when we go through that FOIL process, so we just have to multiply the first and the lasts. So this square root times the same square root would cancel out, and we're just left with the insides. Then we have the last square root times the same last square root would cancel out, and we're just left with those insides. But notice how we have a negative times a positive, so we would have to subtract those together. Checking out the bottom, we do not have a conjugate, so we'll just keep those terms separate, because hopefully something will cancel out, just like it always does. So if we take a look at what we have left, maybe we can start to simplify, make our life a little easier. If you were to distribute in the negative, notice how we would have a negative x and then a positive x, so those would go away. We would also have a negative 2 and a positive 2, so those would go away. So we're essentially just left with an h up top, and if we take a look at our fraction a little bit further, we do have the single x being multiplied on the bottom, so that would cancel out as well. So since everything canceled out at the top, we just have a placeholder of 1, and looks like we're left with the conjugate in the denominator. So since a lot of things canceled out, let's try direct substitution again. We'll plug in 0 for h, so we're left with 1 over the square root of x plus 2, because that h went away, and then we have another square root of x plus 2. Since they're the same square roots and we're adding them together, technically we have 2 of them, so we can write 2 square roots of x plus 2. So there's our derivative. This is representing the slope of the graph of f of x at any tangent point that you want to pick. Alright, so let's go ahead and now check out a rational example if we have a fraction. I'm going to go ahead and erase this conjugate that kind of went over into that, so hopefully you have that set up on your paper as well. So let's go ahead and apply our derivative limit to this function. Okay, it always starts off the same way. H approaching 0, we want to plug in x plus h in for the x's in the function, and we still have the plus 2. We're then going to subtract the original function, and that's all over h. Now, taking a look at this one, we have fractions galore, so we're probably going to have to use some properties of fractions. If we're going to subtract two fractions together, we're going to have to get a common denominator first. So looking at our denominators, they are a little complicated, but we can simply multiply by the opposite denominator in order to get that common denominator. So what I mean by that is we're going to have to multiply the first fraction by x plus 2 on top and bottom, because that was this opposite denominator. And for the second fraction, we'll have to multiply by x plus h plus 2 on top and bottom to get a common denominator. So let's see what we have left. So if we multiply 3 by x plus 2, we can distribute in that 3 and get 3x plus 6. If we were to distribute in a negative 3 into the other numerator, we'd have negative 3x minus 3h minus 6. So this is our new numerator, and then we're going to keep the common denominator, which was the x plus h plus 2, and then another x plus 2. Don't forget that this is still all over h. So it seems like a lot, but notice how we did simplify these two fractions because now we only have one fraction left. Let's see if anything's going to happen. So we have a positive 3x and a negative 3x, positive 6, negative 6. So that's nice. We're just left with a negative 3h over the common denominator. And perhaps instead of dividing by h, we can bring that up and multiply by the reciprocal of h, which would be 1 over h. And that might be beneficial for us to do because notice how the h's will now go away. So we're left with, let's see, negative 3 times 1. So negative 3 up top, and then the common denominator in the bottom. All right, so I would say a lot of things canceled out. Maybe we can try direct substitution now. If h is going towards 0, okay, so this h is going to disappear. We're left with negative 3 over x plus 2 times x plus 2. So maybe you want to write that as negative 3 over x plus 2 squared because you're multiplying the same thing together. So this is what our derivative is. This equation is representing the slope of a tangent line at any location that you want to pick. So they can be kind of simple, like the linear and the quadratic one that we had at the beginning. Sometimes they can be a little bit more complicated, like a square root or a fraction. But I'm thinking these actually are not going to be that bad because there's still limits. And we spent a heck of a lot of time dealing with limits in the first unit. And we got really good with using limits to help us solve square roots and rational functions. So now we're just applying it to this idea of a derivative where we're going to substitute in x plus h first, and then we'll subtract the original function, and that's all over h. So we're just applying this general formula to that happens to be a limit to help us figure out the derivative of a function. So now that we know what the derivative is for both of these examples, let's go ahead and see if we can write the equation of a tangent line. So for a tangent line, or for any line really, we need a point and a slope. The point is going to come from the original function. So if you were to plug in x, what would the y be? So if we plug in 7, we'll get the square root of 9, which would be 3. So x value of 7, y value of 3. The slope of our line comes from the derivative. Remember, slope or derivative means slope of tangent line. So in our derivative that we found above, we're going to go ahead and plug in 7. So we would have 1 over 2 times 3, which would be 6. So now that we have a point and a slope, we could simply write our point-slope form equation, and we'll call it a day. You can leave it exactly like that. Okay, point-slope is going to be your new best friend this year. Let's try the same thing for the rational function. Equation of a tangent line, we need a point and a slope. So point comes from the original function. We'll plug in 1, 3 over 3 is 1. Slope comes from the derivative. So if we plug in 1, 1 plus 2 is 3, square it, we get 9, negative 3 over 9, negative 1/3. So point slope form equation, y minus 1 equals negative 1/3 times x minus 1.